So seeing this diagram here of an elevator falling attached to a spring, and the question says, a 1,000 kilogram elevator is falling at 4 meters per second due to a broken cable. The spring cushions its fall, bringing it to a stop after 1 meter. If friction force during its fall is 9,000 newtons, what is the spring's constant K for it to allow it to stop 1 meter later? The situation involves both gravitational potential energy and elastic potential energy. So if you remember our energy equation here, where K is the kinetic energy and U is the potential energy, how does this equation change when both elastic and gravitational potential energy is involved? To find this, we can use the work energy theorem, which states that the total work is going to be equal to the change in kinetic energy. So what's the total work going to be for our situation? It's going to be given by this here, where we have the work due to gravity, the work due to the elastic potential energy, and the work other, which is the work due to any other forces. In our case, it's going to be friction. And previously, we know that work gravity is equal to the negative change in gravitational potential energy, also given by these two forms here. Additionally, we know that the elastic work is equal to the negative change in elastic potential energy, also given by these forms here. We can apply this to our work energy equation. If we sub in these values, we can plug this into our general energy equation by bringing K1 to the other side, and we can see that the K2 minus K1 is equal to this expression here, so we can plug it in and simplify, and we arrive at this equation here. So this is our energy equation when we have gravitational contributions, spring force contributions, and friction / any other force contribution. This is going to be the energy describing the system. Apply this to our example. So this is our example here, and this is our energy equation. We can take point 1 as the bottom position of the elevator. This is going to be y equals 0. Take point 2 when the elevator stops after the spring compresses a certain amount. We can apply that U gravity is equal to mgh, and the potential elastic energy is equal to 1/2 kx squared. We can plug these into our energy equation and we get this. Then we can identify our variables. H1 is going to be equal to 0 since we took the initial height as 0. X1 is going to also be equal to 0 because we can assume that the spring initially starts at rest. Initial velocity equal to 2 meters per second. Final height H2, that's going to be negative 1 meters because it's falling by 1 meters. X2 is going to be equal to H2 since the spring is compressing, so it's going to be negative 1 meters. V2 is equal to 0 meters per second because the object comes to rest. What we're trying to solve for is our K constant, so we can plug all these in and then we can do some simple computations, and if we do that we get this here. One thing we need to figure out is what work other is. This is going to be the work due to friction. Apply our general work equation, which is equal to force times displacement. If you look at our diagram, our friction force is going to be pointing up and then our displacement is going to be pointing down. Also write the work is equal to the amplitudes of force and displacement times cos theta, where theta is the angle between them. And if you do that and plug in our values, we get this. It's going to be the work due to friction throughout its motion. Plug all these values in and then we can just simplify for K by first bringing this term to the left hand side and then doing a simple summation. Multiply both sides by 2. You can isolate for K by multiplying both sides by 1/1m squared. Do that and compute the amplitudes in the units. We get this for the final answer. So this is going to be the constant in the spring that allows the elevator to come to a rest after 1 meter.